Hello, everybody. This is it. This is the last of the AP Physics exams. I always do electricity and magnetism last because it's the least number of people take it. So from 2025, this is a service of World's Finest Physics, which is my company. It's our website, and we're going to have the two major services going on: tutoring and maybe some extra practice and other guides for students coming up. We do tutoring now, but we're going to try and do some more free things for students, and then professional development for teachers, and also providing more resources for teachers also for free. So just check every couple of months and see what we got going. Okay. So, electricity and magnetism is the last one. Let's go ahead and do it. I have not done these in advance, so you are seeing me doing these cold. An isolated air-filled charge capacitor consists of two conducting coaxial cylindrical shells. They each have a length L. The inner shell has a radius R1, the outer shell R2, and R1 and R2 are way less than the length. The surface charge densities of the inner and outer shells are those. The absolute values of the total charges are equal. The total charges are equal because it's a capacitor, right? Okay, good. All right, using Gauss's law, derive an expression for the magnitude E of the electric field as a function of the radial distance r in the in-between region. Okay, so here's going to be our Gaussian surface. Our Gaussian surface is going to be a cylinder, all right? And we are going to enclose all of the entire inside like that, okay? So let's just go ahead and let's do AI here. So AI is going to look like this. Integral around a closed surface E dot dA equals Q enclosed over epsilon naught. The electric flux is only going out the lateral. The electric flux is not going out the end caps. So this just becomes E times 2 pi R, generic R, because this is a generic R radius, and then the L is L. Okay, so that's the lateral area of a cylinder. And then this is going to be sigma 1. Remember, sigma is charge per area, and the area here is going to be capital R1. So this is going to be 2 pi R1L over epsilon naught. And then, strangely enough, when you're just going to cancel out the 2 pi and the L, and you just get the electric field is sigma R1 over 2 lowercase r and an epsilon naught, I guess. No, not the 2. The 2 disappeared. So just sigma R1 over epsilon naught little r. Okay. That works out for me in terms of units. Okay, derive an expression for the absolute value delta V of the potential difference between the outer and inner shells. Okay, so what we're going to say here is we're going to say delta V is integral E dot dr. Exactly. Now, I'm going to go from the inner to the outer. So we're going to go from R1 to R2. There's some negative sign in there, but I know that if I integrate from the positive to the negative, then I don't need the negative sign. Okay, so it's going to work out. Okay, so don't worry about it. R1 to R2. This is sigma big R1 over epsilon naught little r dr. So really this is sigma R1 over epsilon naught integral of R1 R2 dr over r. Okay, so this is going to become natural log r. So sigma R1 over epsilon naught, and this will be natural log of R2 minus natural log of R1 when I plug in the bounds. So the delta V is going to be sigma R1 over epsilon naught times the natural log of R2 over R1. Okay, so that was A2. All right, what's coming up here? Sketch a graph of E as a function of R. Okay, I think that's it. Well, why is it 0? Because there's 0 net charge enclosed. How do you know that it's 0 net charge enclosed when you're outside? Because it says the absolute values of the total charge on the shells are equal. So anything out here encloses equal positive and negative. Anything in here encloses nothing at all. So you really have 0, then this 1 over r, then 0. So you have this 0 because there's no charge enclosed at all. Then this is a 1 over r type graph, and then 0 because there's 0 net charge enclosed. I mean, that's my story. I'm sticking to it. Okay, let's see. A material of the dielectric constant kappa is inserted into the isolated charge capacitor such that the material fills this region. Derive an expression for the capacitance C of the capacitor with the material inserted in terms of. So here's what I'm going to say. I'm going to say this. I'm going to say Capacitance is Q over V. This is a Q of one side. Okay. And then what am I going to say? So the Q on the inside is sigma 1 times 2 pi R1 L. Okay, so that's the Q inside. And then the delta V, so that's also the Q on both sides. So that's what I'm going to use for the Q. And then the delta V, I was told, was, what was it before? I just got it. Sigma R1 over epsilon naught. Sigma R1 over epsilon naught, natural log of R2 over R1. So that came from part A2. This also came from Gauss's law. That's the charge. Okay. And then now watch what I'm going to say. I'm going to say that because we filled this in with kappa, kappa is going to multiply into epsilon naught. So anywhere where you have a non-empty space material, kappa multiplies into epsilon naught. So let's just go ahead and divide one by the other and let's see what happens. Sigma 1 times 2 pi R1L over sigma, was this sigma 1? Was I supposed to put sigma 1 this whole time? I think I was. I think I was supposed to put sigma 1 this whole time. Sigma 1 this whole time. Sigma 1, sigma 1, sigma 1, sigma, sigma 1, sigma 1, sigma 1. Stupid bullshit. Okay, over kappa epsilon naught, natural log R2 over R1. Okay, now these two things in the denominator are going to nuke these two things in the numerator. And then the kappa epsilon naught is the denominator's denominator. So this will become kappa epsilon naught times 2 pi L. And then the natural log of R2 over R1 is going to be in the denominator. All right, that's my best guess. All right, we got some magnetism now. A rotating circular conducting loop of area A and resistance R is in an external uniform magnetic field of magnitude B that is directed in the negative z direction in the page. At time t equals 0, the magnetic field is perpendicular to the plane of the loop, okay, as shown in figure 1. Okay. The loop is rotating with constant angular speed omega and period t about the dashed line that's along the diameter of the loop. The value of the magnetic flux is given by that. So they just gave us the flux. Thank you for that. The absolute value of the induced EMF in the loop is EMF. The partially completed bar chart in figure 2 shows the bar that represents the EMF at time 3/4 t. Okay. In figure 2, draw bars that represent the absolute value of the EMF at times 0, quarter t, and 2t. Okay. If e equals 0, write 0 in that column. Okay. So flux. So EMF is d flux d time. So that would then be BA omega sine omega t with a negative. But we're asking about the absolute value of electric field, of EMF. So that would be BA omega sine omega t. Okay. So so let's just really quickly do time equals 0, time 0, quarter t, half t, 3/4 t, and then the value of sine at each of those. Sine of 0 is 0. Sine at 1/4 of his period is like full. And then sine at 1/2 of this period is 0. Because what am I doing? I'm doing this. I'm doing like t. And then sine is like that, right? So at half his period it's 0. And then his absolute value at 1 and 3. So that means that this is the same. And these are 0 and 0. That's what I'm going to say for that. That's really weird. Driving expression for the maximum induced current in the loop in terms of blah. Why do I feel like that's too easy? I just did it. I just said if flux is BA cosine omega t, then EMF is d flux d time, which is now cosine becomes negative sine omega t, BA omega sine omega t, and then EMF equals IR, so that's going to equal negative BA omega sine omega t. So I is going to equal negative BA omega over R sine omega t, and that is maximum current because the highest value that sine can come out with is 1. So BA omega over R. AR, B, and omega. That's what I'm allowed to have. Well, I did that. Okay. On the axes shown, sketch a graph of the instantaneous power dissipated by the loop as a function of t from 0 to t. Okay, so here's what I'm going to say. Power is voltage times current. So that's going to be voltage. Negative B A omega sine omega t times current, negative B A omega over R sine omega t. So in other words, I'm going to get B A omega squared over R sine squared omega. So I need to graph sine squared. I just need to graph sine squared. So here's going to be in orange. 1, 2, 3, 4. Half t, 1t. So sine in orange, and then in purple, sine squared, maximum 0. Negative 1 squared is positive 1. So it's going to look like this. Okay, so now I'm just going to say, I don't have to label anything, do I? It doesn't say I have to label anything. Okay. Indicate whether the sketch you drew in part C is or is not consistent with the bars that you drew in part A. In part A, what did I say? Oh, the EMF. Yeah, yes, they are. When EMF is highest, power, which is EMF squared over R, is also highest. Both A and C show the highest at t equals 1/4 big T period and t equals 3/4 big period. Also, 0 EMF is 0 power, which happens at t equals 0 and t equals 1/2 t. 1/2 t in both A and C. Okay, that was a clever one. I did not know where that was going, and I was very, very happy with it. Okay, in experiment 1, students are asked to use a graph to determine the resistivity rho of a circuit element that is connected to variable power supply, shown in figure 1. The circuit element is cylindrical and has uniform resistivity. The students have access to a voltmeter, ammeter, and ruler. Describe procedure for collecting data that would allow students to use the graph to determine row 1. Okay, so what we're going to do is we're going to connect the ammeter in series and the voltmeter in parallel to the element. Okay, right? So here's your ammeter. Here's going to be your voltmeter, right? Okay, we're going to measure. It says that it is cylindrical and has uniform resistivity. Measure the radius R and length L of the cylinder. Yeah, that's the phone from my kid's elementary school, and I'm in the middle of this video. Okay, I don't know what it means. I'll have to call him back. Let's just finish this up. Okay, so let's see here. Okay, then set the variable supply to different voltages V and measure the resulting current I with the ammeter, and we're going to measure the voltage with the voltmeter, right? Okay. Repeat each trial several times and take an average I or something like that to reduce experimental uncertainty. Okay, now what we're going to do is we're going to plot voltage versus current, and the slope of that is going to be the resistance because V equals IR. So V is on the Y and I is on the X, so R is the slope. And then we're going to set R equal to resistivity length over area, and we're going to solve for resistivity. That was all part B, starting with what we plot and then how we take the slope of the plot and get, that's how you get that. Okay, so that was actually almost an AP Physics 2 level question. Like, it really was squarely AP Physics 2. That was not that complicated. Okay, in experiment 2, students are asked to use a graph to determine the resistivity rho 2 of a solid cylindrical resistors made of the same material but different lengths L. The cross-sectional area of each resistor is that much. The students directly measure the resistance, the length, and the resistance. Okay, so resistance equals resistivity length over area. So if I say resistivity over length, I do this lab with my students, then you get resistivity over area. So then we're going to plot on the vertical axis R. It's even in the right-hand column for us. And the horizontal axis is going to be L. It's even in the column for us. So that almost feels like my intelligence being insulted. Just going to tell you that right now. Okay, that's my wife right now. Okay, let me finish this video really quick and then find out what the devil's going on. 0.6, 2.5, 3.2, 0.24. Okay, so let's multiply L1 times, so something really serious is going on, but I'm in the middle of the video right now and I don't know how to paste two videos together. So let's just plot this really quickly here. Okay, so I'm going to pretend like you know how to plot the data and make a best fit line. Let's just see what it looks like here on the graph right here. Okay, so L1, L2, zoom 9, there it is. Let's just take a linear regression, L1, L2, and so that's just going to be the resistivity over the area. So so 78. So the slope is, I got 78, and that's resistivity over area. Okay, you see that from right here. There's the rise, there's the run, and then this is the slope right there. So, and then what was the resistivity? 5 10 to the negative 6. Okay, so 78 equals resistivity over 5 times 10 to the negative 6. So the resistivity is going to be whatever 78 times 5 e negative 6 is. Okay, so 3.9 times 10 to the negative 4, and the units are ohm meters. Okay, let's do this really quick here. What's going on here? Okay, long parallel wires S and T are a distance 2D apart. Both wires carry equal currents I, but the currents are in opposite directions. Both wires are parallel to the x-axis, and as shown in the figure, sphere 1 is a distance d above wire S. Okay, sphere 2 is a distance d below wire S, and both spheres are moving with speed v in the x direction. Each sphere has positive charge q. All right, F1 is the magnitude of the magnetic force exerted on sphere 1 due to the currents in wires S and T. Okay. F2 is the magnitude of the magnetic force exerted on wire 2 due to the currents in SNT. Okay, so what I'm going to do is I'm going to name this the green wire, and I'm going to say that there is out, 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 in magnetic field. And I'm going to name this the pink wire. So there's going to be in, but not as much in, basically, right? Okay, so F2 is going to be greater than F1, and I'm not going to write out the explanation why, but sphere 2 is in two into the page magnetic fields, and sphere 1 is in a out of the page magnetic field, weakened by a little bit of into the page magnetic field. I derive an expression for the magnitude B total of the magnetic field at the location of sphere 2. Okay, so I think in AP Physics C, E, and M, you have to start with Ampere's law, mu naught I over 2 pi r. So for a straight wire, so then this becomes B times 2 pi r equals, shoot, I didn't mean that. I meant mu naught I enclosed. That was a Freudian slip. Okay, mu naught I encloses I, and so B equals mu naught I over 2 pi r, but B at sphere 2 is twice as much, or B equals mu naught I over pi r, pi d, okay, pi d, since wire S and T contribute the same. B equals mu naught I over 2 pi d in the same direction. Okay, so there you go. So it's twice the magnetic field. Okay, later wire T has current 3I in the positive x direction. Okay, at the instant shown in figure 2. Sphere 2 is a distance d below wire S, speed v is a new magnitude. Okay, is the new force, I think the new force is the same as the old force, and here's why. Because now T's magnetic field is 3B's out of the page, and S's is 1b into the page, right? What am I thinking? I'm thinking B equals mu naught I over 2 pi r. So this is times 3. So T creates 3 times as much magnetic field as S does, and they're in opposite directions. So the net magnetic field is still 2B's, like in part B. Okay, if I made a mistake, especially since I'm under the pressure of what the heck am I getting phone calls about, you are more than welcome to put the mistakes in the comments and correct them.